Okay, so we're going to finish off Chapter 9 here with our discussion of molecular orbital theory, or MO theory. And to get started, just a few definitions. So this is a bonding theory based on the mixing of atomic orbitals of similar shapes and energies to form molecular orbitals that extend across two or more atoms. And so what we'll see with MO theory, it's very similar to valence bond theory, what we discussed last time. However, in MO theory, we really just focus on the bonds between simple diatomic molecules, whereas valence bond theory we use to really describe the geometry about a central atom. And so, of course, a molecular orbital is a region of characteristic shape and energy where electrons in a molecule are delocalized over two or more atoms in a molecule. So recall, delocalization describes when electron probability is spread out over a large region in a molecule. And then a bonding orbital, regions of increased electron density between nuclear centers that hold the atoms together in molecules. And as we shall see, there's some quantum mechanics going on here in that we really view a bonding orbital as arising from constructive interference of electron waves. And recall, constructive interference is when I have two waves being added together in phase to overall result in a brighter spot, if let's say this was light. But in the case of electrons, the constructive interference will result in enhanced probability, in other words, than finding the electron in a specific location. And then there is the anti-bond, or the anti-bonding orbital, which is a region of increased electron density in a molecule that describe the molecule because they decrease the electron density between atoms. And this, of course, is a result of destructive interference, which, again, if I was adding waves together and they were being added out of phase, then the result would be no amplitude or no probability of finding the electron in that region. Okay. So now if I move forward here, so this is what our molecular orbital bonding looks like, and we're going to start with H2, just a simple molecule. And similarly in valence bond theory, we start with one hydrogen, each having a 1s1 electron. And as they get closer, we get this constructive interference. And now what this red region shows you, this shows you the sigma 1s bond. So remember, sigma bond describes the single bond. In this case, the single bond between the two hydrogen nuclei. And we see electron density existing between the two nuclei, okay? But now we also accept that the anti-bond is possible. So this is the bond, and this is now the anti-bond. And so what you'll notice is in the anti-bond, there's no density, there's no electron density or electron probability existing between the two nodes. So that's why we call it an anti-bond. Okay? And so if we were to put this together in a diagram, the same way we did electron orbital diagrams, or I should say atomic orbital diagrams rather, we can put together an MO diagram, a molecular orbital diagram. And we start by having the individual atomic orbitals. So we can see over here, these are the AOs, the atomic orbitals, okay? And each hydrogen is a 1s1 and a 1s1. And when these come together and make the sigma 1s bond, which sigma being single bond formed from the 1s electrons, this lowers the energy of each hydrogen. This is why they form. There's the mutual benefit to forming this bond. And recall, this was from our potential energy diagram, right? When I have two really separated nuclei they don't have much potential energy between the two, but as they get closer and closer, right? So maybe like right here and right here, there exists a sweet spot, right? Which lowers the energy overall. So that's what we see in the MO diagram. There's a lowering of energy. And then finally, when we want to populate the MO diagram, we recognize we have one electron in our atomic orbital, another electron in our other atomic orbital, and one electron makes two electron pairs. And so it's predicted hydrogen will have one sigma bond and no antibonds. And this makes the hydrogen molecule very stable. Okay. But if, for example, we were to start adding electrons to this hydrogen molecule, if we were to make an ion out of it, we would end up populating those electrons into this upper level. Okay, so we'll go to that in a second. But for now, let's get a picture of what these molecular orbitals look like. Okay, and so we're going to start building these bonds, these molecular orbitals, by moving up the table in order of energy, starting with 1s, and then we could go to 2s, and then we could even go to 2p. I'm not showing you 2s in this picture because it looks very similar to 1s, but we'll see why 1s and 2p are significant here. So again, if we add two 1s electrons to each other, we can make the sigma 1s bond, and the result is the same if we were to do 2s electrons, and we would just call that the sigma 2s bond. Okay, and it looks very similar. It's kind of a cigar-looking hot dog shape, where each of my nuclei would be right here, and the red shape indicates electron density between the two to make a molecule. So we encountered the pi bond when we discussed valence bond theory. So recall when I have a 2px and a 2px, or a 2py and a 2py, I get the pi bond. And the reason for the notation of the x and the y is because I'm going to specifically define the internuclear axis, so this line right here, as the z-axis. And similar here in this picture on 2py, I'm going to define this space in between the two orbitals as the z-axis, and that's just something that's done customarily in molecular orbital theory. So we recognize that this 2px and 2px and 2py and 2py is what we called our off-axis pi bond when we were discussing valence bond theory. And so in this pi bond, right, my two nuclei would be right here or right here. And so these pi bonds describe the double bond, right? That's off axis from the nuclear axis, okay? But now, the reason why this is important to define x and y is because now, if we look at the 2pz, and again, here's my two nuclei, and so I've defined the z-axis as such, we can see now that you would actually get electron density existing between the two nuclei, and that's a sigma bond, okay? So my two nuclei would maybe be something like right here and right here, okay? And so it's a sigma bond because it's electron density existing between the two nuclei. And there are these two lobes, some small finite probability of being found outside there. However, this is important to note that we can make a sigma bond from 1s, we can make a sigma bond from 2s, and we can make a sigma bond from 2p, but that's specifically a sigma bond from 2pz, okay? And similarly, if we were to look at these antibonds, now we could really view this as 1s minus 1s for the destructive interference, and this is our sigma 1s star bond. That star means anti, so let's write that down. When we see the star there, that refers to an antibond. Okay, and so what's important to note here, right, there's my two nuclei. There's no electron density between the two nuclei. So an antibond would describe a destabilized or even non-existent molecule. And similarly, if I have a 2px minus a 2px, I get this shape where my two nuclei would be here. No electron density between the two nuclei. And 2py minus 2py would give me the same thing. And then my 2pz minus my 2pz, because remember, z is my internuclear axis. This would also result in no electron density between those two nuclei, which would describe, like I said, a non-existent molecule. There's no electrons holding these two nuclei together. Okay, so moving on. So now if we wish to start constructing our MO diagrams for our molecules and we want to build these up, so we described the hydrogen already, and I'm going to zoom in on this for you guys here. Okay, so here is my H2MO diagram, and remember, we start with an H1s and an H1s, the atomic orbitals and a free H atom, and there's an electron in each one of these, and so those electrons then get paired up to form the sigma bonding orbital. So, but now suppose that we had, let's see, I'm going to draw that with a different color pen, so maybe that it shows up better for you guys. Well, we'll do it for the next one. So now, imagine if we had H2 minus. So that's going to be hydrogen with one extra electron, which means there's 3 electrons to distribute in this MO diagram. Well, it doesn't matter which one you say has 2, but one of them would have 2 electrons, and the other would have 1 electron. Okay, and so when those get paired up, we have 3 of them that need to get paired up, and that would go 1, 2, 3. And so now my H2 molecule has been destabilized because it's got 2 electrons in a bonding orbital, but 1 in an anti-bonding orbital. And we'll see what the manifestation of that is momentarily. And then finally, if I were to do helium-2, which overall will have 4 electrons, 2 electrons in each helium, I now have 4 electrons I need to populate in this molecular orbital diagram, and 2 of them go in here, and then 2 of them go in here to give me my 1, 2, 3, 4 electrons. So again, these are from the atomic orbitals, and these are from the molecular orbitals, okay? And so the question on the page is, does He2 exist as a real molecule? And it does not. You would not find He2 as a real molecule, because if it's got 2 electrons in a bonding orbital and 2 electrons in an anti-bonding orbital, these 2 things cancel each other, and we couldn't expect to find any He2. And so that leads us to something I'll define as bond order, which is the number of bonding electrons minus the number of antibonding electrons divided by 2. And what this tells us is the number of bonds in a molecule, or the number of bonds that exist between 2 nuclei. And so when we look at this He2, we recognize that, again, there was 2 electrons in the bonding orbital and 2 electrons in the anti-bonding orbital. So for my bonding order, 2 minus 2 divided by 2 equals 0. And because that equals 0, that tells me helium-2 can't exist. That's another way of saying that, okay? So now, let's move on to more complicated molecules. And as we move past helium and into our row where we expect 2p to be a possibility, we have to construct this diagram. And let's talk about it from the ground up, okay? So, for example, and we'll start here on the left picture, and I'll tell you about why the picture on the right is different. So now, if we start at 1s, okay, we remember everything on these sides are atomic orbitals, and everything on this side is also an atomic orbital, and everything in the middle is the molecular orbital. And so we can see that 1s and 1s makes sigma 1s and sigma star 1s, and 2s and 2s does the same thing. But now once we get to 2p, it gets more complicated. And remember, when we're at 2p, we can make pi bonds. We can make double bonds. And so if we start counting up how many positions that we need, well, if I have 1, 2, 3 positions over here where I can get 6 total electrons, and 1, 2, 3 positions over here where I can get 6 more electrons, I should be able to get 12 electrons in this entire diagram. So let's count that up. So if I have 1 pi bond, that would only be 2 electrons. So in reality, what I need is the possibility for 2 pi bonds, or 4 electrons. So 1, 2, 3, 4, 5, 6. And then now I could make 7, 8, 9, 10, 11, 12. So in other words, if you notice here, I've got a position for 2px and 2py to make the pi bond. I have a position for 2pz to make the sigma bond. And I have another position, I don't know why I drew lines through that. And I have other positions for the 2px star and the 2py star and the 2pz star. So overall, that gives me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 electrons, because again, I would predict that I need 6 and 6 or 12 electrons in total to populate this diagram. And so now if we compare this one to this one, we notice that the 1s and the 2s MOs are the same. And now if I start looking at what's happening here, the position of the pi bonds switched with the position of the sigma bonds. Because as it turns out, some molecules will have pi bonds that are lower in energy than their sigma bonds, and some molecules will have sigma bonds that are lower in energy than their pi bonds. And there's a real easy position on the periodic table to know where this happens. And I won't expect you guys to know this in too great of detail, but if we look at the examples of N2 and O2, we can begin to see where this switching arises from. Okay, so here I've got the nitrogen molecule N2, and here I've got the oxygen molecule O2. And you can see on the left and the right of the diagrams, the atomic orbitals are described. And recall for nitrogen, for its valence electrons, that would be 2s2, 2p3, right? And we also have the 1s molecular orbital available, but it hasn't been shown here. It's only showing you the valence electrons. And then similarly for oxygen, the valence electrons are 2s2, 2p4, so that's 1, 2, 3, 4, okay? And so now when we go to populate this diagram, we note that our sigma 2s and sigma 2s star are filled up, right? I've got 1, 2, 3, 4 electrons here, so 1, 2, 3, 4 here. So these are all filled up and don't contribute to bonding. But now if I look at what's going on over here at the 2p level, I have 1, 2, 3, 4, 5, 6 electrons to populate on this diagram, and they get filled in as 1, 2, 3, 4, 5, 6. So there's, see if I can draw this and have you see it. 1, 2, 3, 4, 5, 6. And this really predicts nicely what is predicted in Lewis structure, where nitrogen has the triple bond, and that would be 2 pi bonds and 1 sigma bond, right? Well, here they are. Here's your 2 pi bonds, and here's your 1 sigma bond. Okay? And so that predicts nitrogen to be a very stable molecule. And the reason why the pi is lower in energy for nitrogen is because it has a half-filled p shell, which is very stable, and that leads to having more stable pi bonds. That's kind of the general accepted idea behind why the pi is lower than the sigma. But now if I look at oxygen, okay, let's first fill out the diagram, right? I've got 1, 2, 3, 4, 5, 6, 7, 8 electrons to fill in, and that goes as 1, 2, 3, 4, 5, 6, 7, 8. And we say, well, isn't the Lewis structure of oxygen like this? It has 2 bonds, and the answer is yes. So how do we predict that? Well, remember, bonding order is the number of bonding electrons minus antibonding electrons divided by 2. So that would be 1, 2, 3, 4, 5, 6 bonding electrons minus 1, 2 antibonding electrons, all divided by 2 equals 2. And there's my double bond. Okay? And so for nitrogen, right, that would have been 1, 2, 3, 4, 5, 6 minus 0 divided by 2 to give me 3. Okay? And what's also kind of neat is this predicts that oxygen is a di-radical. It has 2 unpaired electrons right here, which is kind of subtle, but it's what describes the reactivity of oxygen. Oxygen is fairly reactive, as you may have guessed from its ability to induce combustion. Okay, so moving along, if we now look at the series, I'm going to show you this full series, and then we'll talk about a few other things predicted by this diagram here. So notice here on the left, in order, we've got sigma 2s star, and then here pi, and then sigma, and then pi star, and then sigma star. And that's how we describe nitrogen, right? And the reason for that was because the half-filled atomic orbital, the half-filled 2p atomic orbital, stabilized the pi bond. And that is true for the C2 molecule or even the B2 molecule, where you can see the order of the pi comes before the sigma. But now when you go to the O2, right, the sigma bond becomes more stable for oxygen and also for fluorine. So sigma becomes lower than pi, okay? So I do expect you to know that the switch happens between the nitrogen molecule, the N2 molecule, and the O2 molecule. So now let's look at a few other things that are going on here and a few definitions, okay? As it turns out, MO theory predicts magnetism. So ferromagnetic, so this is a material that contains unpaired electrons and is permanently magnetic. So this is typically most magnetic materials you might encounter, like the magnets on your refrigerator are ferromagnetic. There are 2 other types of magnetism. One's called paramagnetic, the other is called diamagnetic. So paramagnetic is a material that contains unpaired electrons and is only magnetic under an applied magnetic field. When the field is turned off, the magnetic properties become unimportant. Okay? And so that's different than ferromagnetic, because ferromagnetic is permanently magnetic. So it doesn't matter if you're applying magnetism or not. And then diamagnetic is a material that contains no unpaired electrons and is not magnetic or very weakly magnetic under an applied magnetic field. Okay? So ferromagnetic is permanently magnetic. Paramagnetic is magnetic only under a magnetic field. And diamagnetic is not magnetic. Okay? So now if we look at this, this is kind of cool, because what we can see here is B2 contains unpaired electrons, and thus it is paramagnetic. We can also predict that it has a bond order of 1, and we get that from the bonding electrons. From the bonding electrons minus the antibonding electrons. We predict that C2 is diamagnetic and has a bond order of 2. N2 is diamagnetic and has a bond order of 3. And all of this we would have predicted from the Lewis structures. O2 has 2 unpaired electrons. It's a diradical, and that makes it paramagnetic with a bond order of 2. So this is actually really cool. If you have liquid oxygen, and you should look this up on the internet, if you have liquid oxygen and you pour it over a magnet, the liquid will actually bend with the magnetic field. It's kind of a neat demonstration. And then F2 is predicted to be diamagnetic with a bond order of 1. And all of these confirm what is predicted with Lewis structure. So it's kind of a neat pairing. And then finally, the last thing we'll discuss, just very, very briefly, everything that we were just describing was from a homonuclear diatomic. If instead we have a heteronuclear diatomic, such as HF, or even something like NO, then the way we adjust this diagram is by noting that the more electronegative element typically has somewhat of a lower energy relative to the more electropositive element. So you notice the oxygen atomic orbitals start with a slightly lower energy than the nitrogen atomic orbitals. And this is all qualitative if you were drawing this diagram. But for a molecule like HF, this one gets kind of hard to predict. But we note the Lewis structure of HF is just this linear molecule with 1 bond. We call that a sigma bond, right? And so that sigma bond is actually made from mixing the 1 s electron in hydrogen with one of the 2p electrons in fluorine. And of course, that's got to be the 2p Z electron to give us the sigma bond. And that's all I'll really say with respect to the heteronuclear diatomics. And any other molecule that's similar to NO or HF, we could just adjust these diagrams appropriately. Okay, so that wraps up our lectures on Chapter 9.